To introduce Professor Biegler. He comes to us from Carnegie Mellon. A couple of notable things about Professor Biegler are that he is the department head there at Carnegie Mellon, and he has many research interests that cover a wide span of research topics in optimization and in modeling, particularly in dynamic optimization, and using differential and algebraic equations to solve problems. Now, a couple notable things about Professor Biegler. I was just talking to Peter before class. He was doing his homework using IPOpt to solve his homework, and he got a solution. Did you not? Okay, good.
Okay, good.
So, Professor Biegler.
At least one.
So, because of IPOpt and other algorithms that he's done, his research has really influenced and affected a lot of different groups. When I was at Exxon, we used IPOpt extensively to optimize chemical plants and refineries. I remember one time we were talking on the phone, and I said, we're having this particular problem, and he's like, well, have you considered this? And it worked. It worked really well, and so it helped our problem at Exxon. Let me just go through a couple of the awards that he's received. Most notably, maybe, is the National Academy of Engineering in 2013. He's a fellow of AICAG in Siam. He's also received the Lewis Award, the Walker Award, and Computers and Chemical Engineering Award, all from AICAG. And then also the Curtis McGraw Research Award, Cash Computing Award, and the Informs Computing Prize. So with that, let's go ahead and welcome Professor Biegler.
Okay. Thank you very much, John. It's a real pleasure to be here. John and I have known each other for a long time, and I remember, he visited us about a year and a half ago, something like that. So I was very glad to learn more about BYU during his visit, and it's really a nice pleasure for me to be here, learn a bit more about the department, make some new friends, and basically get to know what BYU is like. I really enjoyed my day here, so thank you very much for the invitation. I'd like to share with you a few things that we're doing in research, and I came up with maybe a presumptive title here, a presumptuous title about new paradigms, and I'd like to share with you some ideas, okay? And some of them are new, some of them are not, but I think for those of you that are not familiar with using optimization as a tool for doing engineering, design, operations control, I wanted to share with you some new ways of thinking about the problem. And so to do that, let's get started with this idea here. Let's see if we can get this to work. Okay. No? Okay. Well, we can do it this way too. No, we can't, huh? Yes. Okay, so to start, what I'd like to do is start with the question, why optimize? Okay? So this is something that we all do. Okay, it's a decision-making tool that we have in our daily lives. And the way we do it is actually probably kind of experiential. We run case studies, we think of scenarios, all of those things happen. And yet what happens is, if you think about this in terms of what is done with a mathematical program, this is not something that this is something that we can do in a more automatic way. And that's what I wanted to talk about and get you to see what the state of the art is. Then I want to talk a bit about a particular way of doing equation-oriented optimization for dynamic systems. And I'll give you kind of a big case study that will give you some idea of what can be done there. Then I want to talk about multi-level optimization and give you an idea of what you can do that is kind of unusual for chemical engineering systems, that goes beyond the envelope of what we're taught in class and what we usually are faced with when we have to do engineering studies. Apply that to case studies, and then the last paradigm will be this seemingly, this challenge of saying we always are faced with a set of models that are not necessarily of the same type, especially when we think about how they're implemented on the computer. Some things are very easy to extract information of, some things are quite difficult and take a long time to solve. What we want to do is figure out whether the best optimization tools can be used even in the case where we have difficult black box models. And so I'll conclude with a case study that shows you how we can marry the two based on some of the recent advances both in derivative-free optimization and in large-scale nonlinear programming. So talk a bit about that. And what I wanted to do is start with just a quick introduction. Why do we optimize? Well, usually what we do is we take the plant, we build a model of that plant, a differential algebraic model, and that model is going to have some degrees of freedom with it. They may be profiles in time, or they may be just some model parameters. And then what we do is we think about running case studies on top of that. And when we get tired, we say, I've got the optimum. Okay? And so at that point, what happens is we give up. Okay? And we say the optimum, we've optimized it. Okay? And so this is a very overused word. You know, everyone optimizes something. But when you optimize something, you want to have some reassurance that you've really not overlooked anything, that you can say with some, you know, under certain assumptions, that you have the best solution, even if it's only within a neighborhood around that point. And so that's where we want to go with optimization algorithms. Okay, so this is still the paradigm that people look at when they think about doing optimization. And this has some advantages. For example, gives better results than with experience, and you've got consistent results among all practitioners. Okay, it's not where, you know, the old guy in the corner can get a better solution than the young guy there. If they apply the same tools, they get equally good answers. But I want to go beyond this. I want to basically look at what happens when you marry the two and think about embedding the model in an optimization problem. And this is important because now you're going to go beyond simulation to actually an automatic decision-making tool. And that decision-making tool should not take a long time to solve. You shouldn't have to wait forever to run a bunch of cases before you get a result. You should be able to run this very quickly. And if you're able to embed this model and solve it within the optimization problem, with some objective function here, and then the model as part of that problem, then you can reduce the solution time by orders of magnitude, and then you can use that not just to get consistent results, but then ask what-if questions, lots of them. You know, what happens, you can support and enhance your understanding of the process, not just by finding a solution, but the best solution under certain circumstances, which you can dictate, okay? So that's the whole point of doing this. Now, how do you do it, and what has happened in the meantime? Well, what you have is there's an evolution of optimization tools that's happened over the last 30 years. I mean, if you start going back to the 80s, there's a very popular algorithm called successive quadratic programming that was used for flowsheet optimization. It's used in Aspen Plus, it's still there, and it usually is limited by about 100 variables and constraints. More recently, there's something called RSQP, which is basically a decomposition of the large-scale version of SQP. And that takes you up to about 100,000 variables and constraints. And that's used for real-time optimization, where you really need to have a fast turnaround. Yes?
So when we're talking about using that many, so many variables and constraints, is that limit like within a reasonable amount of time? Is that how we're defining that? Okay. So,
yeah.
Because in theory, you could do as many variables as you want, but it would take too long.
Oh, no, we're not talking about decades.
Right.
We're not talking about eons. We're talking about the time that you would wait to get a solution for a simulation. Okay? And that's exactly the idea. Optimization should not be any longer than a single simulation. All right? Now, it gets interesting when you're talking about CFD problems, but we'll get there. Okay? All right. Then what happens is, at this point, we're talking about doing a little bit more than just this evolution of SQP. Basically, what we're doing is developing programs that are completely open. And now you have problems where you can solve millions of variables. And in fact, this is something that was developed in, basically 10, 15 years ago. More recently, there's a sensitivity component of that, where you can now take the solution of this problem, very large, and find neighboring solutions very quickly, in let's say under a second. Okay? So those are the kinds of things that we're building on when we think about these new paradigms. Now, the other point that is equally important is not just the algorithm, how you solve this problem, but the environment in which you model this problem and access the algorithm. Okay, and for this, what I want to mention is the most efficient tools now handle millions of variables and constraints with modest computational effort. And for this, you'd basically take tools down here and exploit structure, which I'll show you in a moment. But the other thing I wanted to show you is this. What's the environment in which you use these tools? Well, think about the model that you have on which you want to do optimization. You can start off with a black box. You can extend that by getting some kind of derivative information with finite difference. You can go and get exact first derivatives, perhaps through a sensitivity or an adjoint procedure. And then you can also go to the last phase, where you have a fully open structure, where the optimizer can see all the equations, all the variables, get the exact first and second derivatives, and that's exposed to the algorithm. And now if you look at things like the problem size that you can handle and the computational efficiency, you can see how it goes up, but it only goes up because you are pairing the environment that you're in with the algorithms that you're using. Okay? So in this case, what we're looking at is down here, if you have only input-output information from the optimizer, then you're not going to be able to use the fastest. You don't want to use an algorithm up here. Derivative-free optimization is probably going to perform as well as anything else. If you get more information over here, like finite differences, and there's no structure given to the optimizer, then routines like SQP are going to perform as well as anything else. So in this case, what we're talking about down here is something that you'd see in MATLAB, basically with either with finite differences or exact first derivatives. If you can now explore it to go to exact first and second derivatives, then you can take advantage of some of the much larger programs like the NLP barrier or programs like IPOpt. And those are the things that are very important. They have to work together. Otherwise, you're not going to see the big benefit that you want. It's like taking a 4-cylinder engine and putting that, and basically putting that in a large truck. When you have this application up here, and first of all, if you take a truck engine and you put it on a tractor, and it's not going to work the same way. So they have to be mated together. So let's talk about some case studies. So the first thing I'd like to do is talk about dynamic optimization. Okay, there's several people here in this room that have actually done quite a bit of work on dynamic optimization, primarily in John's group. And what I wanted to show you is a little bit about how this evolves when you use the right tools. So here's the dynamic optimization problem. What you've got here is you've got a differential algebraic system that looks like this. You've got an objective function, and you have differential and algebraic state variables. You have control variables over here and some parameters. Okay, so that's the problem that we want to solve. And if you look at the dynamic optimization problem, this has been well known for centuries. But it starts with the calculus of variations. And going back 60 years, you have Pontryagin's maximum principle, okay, and variational approaches that were used to solve this problem. Then if you get larger problems, you realize that you need to handle constraints, you need to discretize something. And so what the first thing you would do is discretize the control variables and then apply some kind of nonlinear programming or nonlinear optimization solver, and that's known as single shooting, where you embed the dynamic model within the optimizer. You can do better by taking a simultaneous approach. And the reason for doing this was recognized early by saying, well, if this model that you want to optimize blows up midway in between, becomes unstable, well, you have to pick up the pieces and try again. The simultaneous approach, you don't have to do that. And so multiple shooting was a way to handle dynamic systems that are unstable. An approach that doesn't require any integrator at all and doesn't require any embedding is one where you throw everything into the optimizer, discretize the states and the controls, and solve that all at once, okay? And this is what we call the simultaneous collocation approach. Now, if we look at this kind of approach, it's a very big problem, so we need the right solvers to handle it, okay? We also can handle a number of challenges like periodic boundary conditions, multi-stage formulations. We'll take full advantage of the open structure. So here's the example I wanted to show you. Now, this is basically manufacture of low-density polyethylene. Okay, so as you can see, polyethylene is all around us, right? It's in this room. Fibers, coatings, or any plastic articles that you have, polyethylene is there. And what you see, of course, is that you make many grades. So one of the things you have to do is run these in large manufacturing systems that require a lot of grades. So here's the process. there's the LDPE process, and the heart of that process is this red rectangle. That's basically a coil reactor that is at 2,000 atmospheres. It's a tube that is about 2 kilometers long and about 10 centimeters in diameter. Okay, so that is where polyethylene is made. You have the monomer, the ethylene, and the comonomers coming in here with the initiators. They go through this 2 kilometers, and then you end up with low-density polyethylene that's removed here. Anything that doesn't react gets recycled back, and recompressed, and goes through again. Okay, so there's the process, and if we take a closer look at that reactor, what we're going to see here is we're going to see ways of feeding in the different ethylene places and cold shots. You have lots of heat transfer going on as the reaction is going on. And then one of the things we're worried about is how do you build a predictive model that will allow you to do some control. Okay, and I'll leave the control part for some other day, but I'd like to show you at least a little bit about how optimization allowed us to build a predictive model. Okay, so let's take a look at this. Again, here are the attributes, and we have multiple zones, and we have high throughput, and now we are trying to figure out a model that handles the inputs and outputs for control and optimization. So what's happening inside the reactor? Well, these are the reactions that are going on. Okay, and what you're building is polymer chains, okay, where each polymer is growing. You have to keep track of each chain in some way. And then what happens is you're building up, you're going through some side reactions. The primary products are here with P, side products are Q, and then you have the monomer here, the monomer that's building up over here. And what's going to happen is this complex set of chains gives you a reactor model with 35 elementary reactions, 100 kinetic parameters, up to 100. And usually this is done by aggregating these in moments so that all the chains can be aggregated through a moment distribution. So you're really keeping track of a distribution of polymer chains. So the real question is, how do you identify this model based on plant data? So what we want to do is start off with an optimization problem that looks like this. We're going to use the rigorous model to match plant data directly, and we're going to start with a standard least squares formulation. So let's take a look at this. What we've got with this least squares formulation is we've got our differential algebraic model over here. We've got measurements that are, well, here what we have is measurements over the data sets, the different zones in the reactor, and the different measurement locations, and those are the temperature measurements over here. You also have endpoint measurements of polymer quality over here, and then of course what you have is the links between each zone. Okay? Now, we've got two kinds of decisions that have to be chosen. You've got parameters in the model that are globally available. These are the rate constants and activation energies, right? They have to be there throughout the reactor. Then you have local parameters, these pi's here, and those are basically heat transfer coefficients, efficiencies of the initiators, things that change from zone to zone, okay, and based on various conditions. So this is the kind of thing that we're going to have to deal with when we put together and fit the data, okay? So one data set, 500 differential equations, 1,000 algebraic equations. If you have 6 data sets, you have that much more, 3,000 ODEs and 6,000 algebraic equations. So now let's take a look at what happens. We'll solve this problem. It turns out to be a fairly large problem with about 400,000 variables. And if you solve it, this is the solution. And the reason I wanted to show you this is for 2 reasons. What you have to do is simultaneously estimate the global parameters and the local parameters. So what's happening on in each zone depends on the global parameters, and what happens to the global parameters is going to be affected by what the data are in each zone. So we have to put this all together and solve this as one large dynamic system. So if we do that, this is the difference that you see. If you take the base case where you fix the global parameters and then estimate the local parameters, you're not going to get a very good fit. You get the black line over here, okay? If you do everything simultaneously, you get the blue curve over here, and there you see how well it fits the red data points. Okay, so this is just an example on 2 grades, 2 different kind of LDPE products, But that gives you some idea of what you can do if you can solve everything together. Now let me expand that a little bit and talk about an advanced method where you usually think a little differently about the problem. So the problem here is two kinds of formulations. The first is standard least squares. So that one I think we can all relate to, right? What you do is you take some data at different input conditions, and then what you do is you measure the data and you assume that all the error are in your measurement, right? Well, if you take this a little bit further and say, wait a second, I've got outputs, my measurements, and I've got also inputs that are governed by an actuator, okay? And that actuator also has error in it, okay? So in this case, both the inputs and the outputs have error that I have to take care of in my least squares function. So instead of just the standard least squares that considers the outputs, I'm going to add the effect of the inputs in there as well. Okay, so now, because I have to deal with both, every measurement or every input is an extra degree of freedom in the optimization problem. So this is what's called the errors in measured variables problem. Okay, so there the number of degrees of freedom is not just the number of parameters over here from the model, it's also all of the input parameters. Now you can think, is this a good idea? Well, if you believe the statistics and you look at the maximum likelihood function, then what you're doing with that is you're actually considering where all the uncertainty is. Okay, so here, this is what happens. If I put together 20 grades and I look at the operating data from the plant, the base model, which did do the simultaneous estimation, is given in black. And you can see that that has a deviation of about 12%. The simultaneous standard least squares problem is 2.5%. And then the results that we got when we had errors both in the inputs and the outputs, that went down by a lot, by 0.12%. Okay? Now the big question is here. How much time does it take to solve the optimization problem? Okay? So this is the problem size. Okay? And actually for for 6 data sets, this is not too bad. Okay, so this thing here has 68,000 variables and constraints. Okay? About 200 degrees of freedom for standard least squares, 500 degrees of freedom for EVM. Number of iterations is not that different, and the amount of time that it takes is about 15 minutes. Okay? Now what I want you to see is that the number of degrees of freedom is more than double here, and still the amount of time that it takes to solve is not that much different. Okay? The reason is actually pretty clear. Second derivatives, and the fact that these are Newton solvers that solve that large optimality condition system. Okay? So eventually, that's what we're taking advantage of to solve this problem. Okay, so this is a problem that 6 data sets, it takes about 15 minutes. If you had only one data set, okay, that's 11,000 variables, that takes only 17 seconds, okay? And what is a little frustrating is when you increase the number of data sets, the time increases more than linearly, much more than linearly. So the question is why? Okay, so this is a little bit disturbing. So let's take a look at why, okay? Well, the bottleneck has to do with the classical thing, which is how well can you solve linear systems of equations. So let's go back to this problem. What we didn't go into, but you'll have to trust me for, is take this problem, write out the optimality conditions, and those optimality conditions can be solved with an extended Newton method. That's essentially the idea behind a lot of modern barrier function methods. Okay, so that's the extended Newton method, and the key to solving that is a linear set of equations based on this problem type. I've aggregated all the variables, put them in this shorthand form, and then the linear system that it's solving is this one. Okay? So it's solving that at every iteration. And it gets really big. It's basically this guy is twice the number of variables. So the largest thing for 6 data sets was something on the order of 130,000 variables and equations. Okay, but now let's take a quick look at that problem again and say, instead of writing it like this, I'm going to write it like this. Okay? So same problem, but now I've taken advantage of the fact that I can separate everything into data sets, into the different parameters, and I know that only the global parameters are the things that are coupling things together. Everything else is separable, okay? So now this linear system, the equivalent linear system, looks like that. Okay, it's the same linear system, but I've permuted the rows and columns to take advantage of this structure. What difference does this make? Well, the difference that this makes is basically that you have this beautiful arrowhead structure that I can start taking apart with the diagonal elements over here. Okay, and when I do that, then I can even use some coarse-grained parallelization. So there's the idea. Now, how do I take this apart? Well, what I can do is I can use each block as a pivot element and then go down each block and then isolate that to create a matrix over here, which is called S. Okay, it's basically just eliminating everything right down to the last row and column. Okay, after that, I'm going to solve that eliminated system for this variable here, and then once I've got that solved, then I'm going to go back and then one by one go back up here and solve for the remaining system. Pretty straightforward. And I can do that sequentially, and I think everyone would agree that if I do that sequentially, the time is going to increase linearly with the number of data sets, the number of blocks. Okay? More than that, this part is parallelizable, right? Because this decomposition here of each block, the pivot, that I can do independently and then sum them up. This one is not parallelizable, okay, but that's a very small part. It's just the global parameters. And then finally, the back substitution, that I can do as well. And that I can do in a parallelizable way. So doing that actually makes an interesting difference because now we can actually run very large problems in very little time. So there's the solution if you do it in parallel. First thing to see is if I don't do it in parallel and I just do it using that structure, then I can see a linear growth with a number of data sets. Okay, so it's much better than what I had before. And in fact, the only problem I have is after 9 processors, I run out of memory. Okay, but if I were to do this in parallel, then what I get is something like this. This is the number of the wall clock time that I have for each iteration as I increase the number of data sets up to the number of the processors. Okay, so that's 32 processors. I can handle 32 data sets. If I have more processors, I can have many more data sets. The wall clock time here is less than 5 seconds per iteration. Okay, and so the total number of time with this is going to be, something on the order of 30 iterations. Okay, so we're talking about 2.5 minutes. The time per linear solve is even smaller, okay, which is here, okay, and that takes about 1 or 2 seconds per iteration. Now this problem over here is 1.2 million variables. Okay, so you can see that in about 2 minutes, 2.5 minutes, I can solve a 1.2 million variable problem, in very little time. So this is the kind of thing that I would call the first paradigm. Taking advantage of the equation-oriented structure and using fast optimization algorithms to get the solution. Okay? Now this is something that I will say has been automated. There are some really nice tools by Carl Laird, former student of mine, and several others that have embedded this into modeling platforms. And so this is something that you can expect to see as one of the new paradigms. Okay, let me go to the next one. Okay, and for this one, what I need to do is pick up a little bit on the pace, but tell you something about modeling in general. Usually when you think about a process modeling, you think about a set of equations, okay? But it's more than that. Many of the models derive from inner optimization problems. So if you think about phase and chemical equilibrium, that basically comes from a Gibbs minimization. Similar things with heat integration. There you're solving a linear program that's embedded within the optimization problem. So we can split those out, and then what we can say is rather than just writing a restricted set of optimality conditions, let's think about the bilevel problem and solve that in a different way. And the way we want to solve this is by using something called math programming with complementarity constraints. So this is the idea. You start with a problem that's embedded within another problem. Once you take that problem, what you can do is you can solve that problem by writing the optimality conditions of the inner problem as a set of equations and then dealing with some terms that are a little more complicated called complementarities. Now these are nasty little things because what happens is they tend to be singular, okay, or lead to singular systems, which is not nice, okay? But what you can do is reformulate them as optimization problems. This is one way to reformulate it so that you can actually solve this as a set of equations, inequalities, and some additional penalty terms. So what difference does this make? Well, I wanted to show you a couple of simple examples. So the first one is this flash problem, okay? So in this case, what happens is cubic equation of state. You can see the cubic roots for the vapor and for the liquid, two phases. There's the equations that we all have in thermo, and there's an interesting thing that happens. What happens if you need to do a flash problem and you're outside the bubble dew point region? It blows up, right? It won't solve. But the Gibbs minimization has an answer, okay? Because what happens is you'll basically have the one phase and you'll know its temperature and pressure, right? We all know this. How do you get these equations to behave like that? Well, what we do is we say, okay, first of all, we know that the cubic roots, they have these properties. You can see they have positive slopes, and the liquid one has a negative second derivative. The blue one has a positive second derivative. We keep those things in there. We can isolate the roots, but then what we do is we say, okay, if I lose a phase, I lose a root. Okay, so in this case, I get something like this, no vapor stream, and in this case, I'm going to add a little bit of a little parameter that will relax the equilibrium condition, okay, and relax some of my inequality constraints. So now I can still model the problem without two phases. I'll still solve the flash problem. More to the point, I can still solve systems that build on the flash problem, like distillation. So here's a distillation column where some of the trays dry up. Okay, I lose liquid on some of the trays. I'm below the minimum reflux ratio. Can I still get this to converge? And the answer is yes. So here's a little example that we did. What you've got here is you've got the standard model of a distillation column, mass, equilibrium, heat, and summation, okay, mesh equations. And what you're going to do is write them down. My equilibrium looked like this, but I replace it with a complementarity model, okay, that looks like this. So let's consider a case where I want to separate a mixture, let's say three-component mixture here, and I want 90% of the high boiler in the bottom and 90% of the low boiler in the top. And so this is the solution of the column. What I have is I have a vapor stream going along here. I have liquid above so this is below the feed over here. That's my liquid stream, and above the feed over here. Okay? So normal solution distillation column. Suppose I do an optimization where I minimize the heat duty, the steam, and I only care about the bottom composition. Okay? So in that case, if I care about a fairly pure bottom composition, then what happens? Well, what happens here is above the feed, there's no reflux, and the trays dry up. Okay? And below the feed, I have my liquid flowing from the feed down the column. Vapor stream is still going on. And of course, the amount of steam that I need is a lot less because it's zero reflux. Let's take the last case. Suppose I don't care about any specs on my product. Okay? What's the minimum amount of heat that I need to run the column if I don't care about the product purities? I think everyone knows the answer. 0. And so certainly that's what happens. In this case, what happens is the column, you pour in the feed, it runs down the bottom of the column as liquid. There's no vapor, okay, and no steam, and the amount of heat duty is 0. Okay? So that's what you can do by extending the scope of the flash problem to handle with these switches and disappearance of phases. That's the complementarity problem. Okay. Similar things you can do with heat integration. And I just wanted to say a few words about heat integration, which is heat integration basically thinks about the problem of matching the hot streams and cold streams, recovering most of the heat, and then what's ever left is used by the utilities. So this is a fairly well-known problem. You do the process optimization, and then you do the heat integration. But that problem interacts with the optimization as well, because your objective function also includes minimization of utilities. So what you really have to do is include this problem embedded within the optimization so that you can do this simultaneously. And that way you get much better embedding of heat. Okay? So that becomes a linear program that's embedded within this problem, and you solve it as a bilevel problem. Okay, so good. Again, you need to worry about the optimality conditions being replicated in this problem. So let me put the two together. This is a problem where you have to worry about distillation and you have to worry about heat integration. So in this case, what happens is you're going to take and integrate an air separation unit where you have to worry about compression costs. The air is free, but then what you have to worry about is providing the refrigeration. And so in this case, what happens when you do that is you want to minimize the amount of energy that you need to do the separation and then figure out how to build that column. So we put all that together. We have trays where there's a disappearance in the trays, and of course, if you have disappearing phases in the trays, guess what? You can count that tray as not being useful in the design. Okay, you can put those together. We put together a problem where we're minimizing the compression efficiency. We have a thermodynamic model. We have the heat integration model. We have hot streams and cold streams, or hot streams and cold streams over here that have to be matched. And then we have a compressor that has to compress the feed. So in this case, we got this solution over here. It's the final solution. It decides on the number of trays. We got a really good solution. The typical problem size was 15,000 variables, 260 degrees of freedom. And then after a nice bootstrapping process where we solve about 10 optimization problems, we can get a solution in about 15 CPU minutes. This is the whole design cycle to give you the ASU. What's nice about this is we compared this with some similar cycles that were developed commercially. We found that they were a little bit better, okay? And so we were pretty happy that this was something we could put together quickly. By the way, if you're looking at how the hot streams in red and the cold streams integrate, you can see there's very little loss of entropy when you put these streams together. They're pretty well matched. Okay. All right, so now let me get to the last part of the seminar, and this is where I'd like to spend a little bit more time and ask a question. By now, I think you get the message that I'm very much biased toward equation-oriented optimization, large-scale systems, taking full advantage of really good large-scale algorithms to solve those problems. We can extend that to discrete decisions like phase changes, like embedded optimization problems. That still is kind of something where we can leverage all the solution strategies. But now let's take a typical flow sheet, and what we find out is that we've got different models embedded with it. When we have conservation laws, we have performance equations, constitutive equations, component properties. Not all of them can be written down as equations, okay? Many of these are black box models that we have to live with because no one is going to stop and rewrite those as equations for us. So the question is, what do we do there? Because the bulk of this system, what integrates everything together, is fully equation based. But there are some models inside that are not. So how do we deal with the integration of those things? Well, we can see those in lots of different areas: physical properties, reactor elements, separation elements, conservation laws. And the question is, can we apply equation-oriented optimization solvers in environments to complex simulation models? Okay? And the answer is yes, if you use reduced or surrogate models. Okay? And how do they work? And what do we have to be worried about? The first thing to worry about with surrogate models is that the optimizer likes to cheat. Okay, and so this is where I want you to see some real cheating in action. Okay, so let's take this model here. Okay, so I want to solve this problem here. This is the original detailed model, my truth model, and it's a very simple simple problem over here. It's the green line here, and the objective function contours are dashed here. What you see over here is that the optimum is here. It's the global optimum. Okay. Now let me fit a surrogate model in red to that point, at that point. So match that surrogate model, which is this guy over here, and B is my tuning parameter. And now what's going to happen is when I do that and solve the optimization problem over here, that's going to move away. Okay? It's going to move away from the global optimum. And then what happens is if I match it again, okay, I'm at this point, and I solve it again, and it moves away, match it again, and eventually I get to this point over here. Okay? That point is where the surrogate optimization model matched the original detailed model, and it's basically an optimum point of that reduced problem, but it's way different from the point that it should have found, which was the global optimum over here. Okay? So it's cheating. What do we do about this? Well, what we do is we have to think about this in a more refined way, where we say the following. Let's use that surrogate model. And we start off at this point over here. What we're going to do is we're going to fit a reduced model at that point, and we're going to take a step and realize that step might not be in the right direction. Okay? So what then we're going to do then is we're going to say, all right, that surrogate model or reduced model might be good within a trust region. Okay? So we'll put in that trust region and solve that again so it doesn't move very far. We'll move it over there. Okay? Once it's over there, then we're going to move to the new point, make sure that, of course, the trust region, make sure that we're improving a measure that gets us closer to the optimum. And then once we move to that point, we adjust the trust region and try again. Okay? So if we do that and go back to our toy problem, okay, then we start, let's say, close to the solution. Okay? We have this trust region, and now we're going to manage the trust region. First of all, we're going to have a surrogate model over here. Notice I have 2 tuning parameters and not 1, and that's actually for good reason. We have to make sure that the KKT conditions are recognized by the reduced model. But once you do that and apply this trust region, then this thing is going to converge, by adjusting the trust region to the global optimum. Okay, or at least to an optimum. Okay? So this is basically what we have to do so that the optimizer does not cheat. Okay? That's the first thing to show. The second thing is, let's take a process here that has a combination of different models. So what we have here is we have both equation-oriented models, and we also have these models here that are going to be black boxes. And so we have, for example, a boiler here for doing fuel combustion. We've got an air separation unit that gives us an oxygen-rich atmosphere. We have a steam cycle, and we have some CO2 separation. Okay? So we put these two together, and we notice that these two guys in the back here are black box models, and everything else here is equation-based. So can we use our equation-based tools to do this? And that's really the question. Well, the way we do that is we start off with this model over here, where we have both the black box and the equation-based models over here, which we call glass box. And what we're going to do is we're going to isolate the black box portion, okay, like this, and we're going to replace this with a reduced model. Okay? When we do this, we can come up with trust region subproblems for the reduced model here, and then that has a few components to our algorithm, including some trust region management. And when we do this, we can prove that we're actually going to get to the solution of the original detailed model, that optimization problem, by adjusting the trust region and going around. So let me show you the problem we worked on. This was going to be our oxy-combustion process. There's the steam side, there's the gas side. We have a boiler here that was originally a CFD model, and that was simplified to a one-dimensional model with 3 dimensions in the radiation components. Okay? So that one we put in with everything else. We made a reduced model of this guy over here that was a linear model, and then we applied our trust region method. And so there's the problem where we maximize thermal efficiency. We did 2 problems. The first one is in an air-rich environment, the second in an oxygen-rich environment. And so now we have a hybrid boiler model in steam thermodynamics, which is our black box model as well. So with the trust region approach and the reduced models, this was the result. It took about 9 hours of CPU time, about 759 boiler simulations, okay, and that was a nice efficiency here. We didn't do anything special with, supercritical compression. So it's actually a nice number. If we do this in an oxygen-rich environment and account for CO2 capture, this goes down to 33%, but 6-point penalty, which is actually kind of a nice number. And again, about 8 hours to solve this problem. So that actually gives you some idea of how we're going to deal with reduced models and guarantee that we get to the solution of the original optimum without having to embed that model in our optimizer. Okay, so where are we going with this? Well, I want you to think of a multi-scale vision where we have reduced models at every level. And that's going to be the glue that ties together all of these different models in an equation-based environment, okay? So far we've combined these two levels. We've done a few cases where we've looked at other levels as well. And so this is kind of a vision that we'd like to pursue, see how far we can push it with equation-based optimization. Let me stop here and just say that there are three paradigms here. Equation-oriented utopia is close to reality. Those are fast tools, they're good environments, and they should be used more. We need to get beyond simulation models to deal with multi-level optimization problems and complementarity conditions. That's a way to expand the scope of what we do for optimization. And finally, we have multi-scale models where we can use some convergent trust region-based optimization strategies where we can use equation-based optimization and deal with black box models. So I'd like to thank all of the people that worked on these problems and the funding, and thank you as well for your patience and for listening. I'd be happy to get any feedback and questions.
We have time just for one or two questions, and then I think another class is coming in, but they can grab you after.
Sure.
Go ahead.
When you're talking about reduced order models,
Mhm.
are you talking about simplifying the physics, or are you talking about the surrogates like Kriging and that kind of thing?
That's a very good. This theory applies to both. Okay, so this is actually something that you know about, Mark. What we need, we've used both kinds of models. Okay, what we need is this property that's called the fully linear property. Okay, so that guy. If you have the kappa fully linear property on the reduced models, okay, which is, oh boy, what happened here? Yeah, if you have this kappa fully linear property on the reduced models, you can prove this method, okay? So what it means is that you don't know the derivatives from the original model, okay? You have a reduced model you're basically constructing from points, whether it's a shortcut model, a physics-based model, or data-driven. But what you have to be able to say is that you can match the model, the function values, response values, and as the trust region shrinks, the derivatives will also, the gradients will also match. Okay, so when you do that, now if you can extract derivatives as well, then of course what that means is you don't have to have the trust region shrinking. But if you can't, you have to have the trust region shrinking in order to make this work. More recently, we've extended this so that we actually deal with a trust region and what we call a sampling region, where the trust region basically guides global convergence, and the sampling region covers this property. And that saves us a lot of time. But that's the theory behind it. The trick is knowing that you can pick the right models. Okay, so, sure.
One last short question.
Yeah.
In the trust region problem show,
Mm-hmm.
does your initial start need to have the actual optimum inside that trust region, or can it move across?
It moves across. It moves across. It doesn't have to be inside. What you're doing is you have to show that the trust region gives you a solution that improves progress toward the optimum. Okay, we use a combination of tricks in a filter method that gives us those criteria. Okay, and then what happens is if the trust region does not show it, then the management says, shrink the trust region, try again. Okay, eventually it has to show it because of some of these properties like this one that mean that you're actually getting the reduced model and the detailed model to be close enough that you have to improve. That's the idea. Okay.
All right, let's thank our speaker again.
Thank you.
We are dismissed.
Okay.